Much of the data we find on the web either comes in or can be converted to, basically it's called CSV format. It's actually a text-based version of what you'll see in an Excel spreadsheet. In this particular case, I have the baseball data giving the list of all 44 players who have hit 50 or more home runs in one season up until the 2018 season. This is in actually Google Sheets format, and I just want to convert it into this CSV format, which makes it a little easier to import into another program. In this case, it'll be the statistics program R. So I click File, and it's download, and this is the format. I could have saved it in an Excel format also. That's also readable in a program like R. If I look over here, this is my Mac, so I'm going to look at my downloads, and here's the program down here, Untitled Spreadsheet Sheet 1.csv. Okay, now we're ready to show how to analyze this baseball data. We've converted the file name to hrgte50s.csv. Now, a few notes about R that you have to remember. Remember a hashtag, I call it a number sign, means comment. If you see a number sign on a line, anything after that on that line will not be analyzed with R. It's just a comment. It's really for humans. So the first thing I want to do here is I want to test to see if the file that I want is in the current directory. One thing that's very important in R is that anything you load in or anything you save is saved in what's called the current directory. If you're using R or RStudio, you can actually get the current directory by going to, well, actually on RStudio it's easy. You look up here and there is the current directory for RStudio. If not, you can go to the console of R and just go get wd, that's get working directory, and lo and behold, there's where we are. Okay, so the first thing I'm going to do, I'm going to check to see if this file is in this directory. I'm selecting an area, and I'm going to press Control Return because I'm using a Mac. If I was using Windows, I could use Control R, and notice my answer down here is true. If I get true, if I don't have true, I have to stop and I have to actually get the directory there, get the file, and put it in the directory. Okay. Now I'm going to really extend line 4. If you have true, then I'm reading in the file from the disk. Here it is. And I'm going to call it hrgte50m. Enter. I didn't get an error, so I must have it. Okay, now I'm going to display the first 6 rows of this particular file, and the command for that in R is head. Head can also be designed to look at the last 6 rows, really any number of rows. If you look over here, you get something that actually looks something like an Excel spreadsheet. Remember, it originally came from this. This is something that in R is called a data frame. What a data frame has is a bunch of columns. Each one has a name. And within any column, the data is of the same type. So you'll have all numbers or all characters. So notice what we have. Later on, we're going to be looking mainly at this particular column, which is the home run column. Now, sometimes character variables, like over here, really aren't character variables. As a matter of fact, when you do this read CSV, many of the character variables are actually converted to what are called factors. We could check that by running a command called str. This is a structure. And let's see what R did. Okay, now let me move this up a little bit. So you'll notice the names were factors. Now, what a factor variable is, it actually gives you different categories. You'll notice that team ID and league ID are also converted to factors, but for the team, there are only 22 different teams. For the factors, there are only 2 factors. Now, for the names, there are actually 29 levels here because we only have really 54 rows. But if we're going to do this for the entire set of baseball players, we would have thousands and thousands of what are called levels. We actually want that to just be character data, which means we can analyze it just like we fiddle around with names. How do we convert that? R has a bunch of functions called as dot, and basically this as character will convert whatever this variable is to a character variable. Now, something interesting. What is this HRGTE50M $ name first that you see up here? Well, you see what the name of the first column is name first, and the whole table or the data frame is called HRGTE50M. The way you access a column in a data frame is the name of the data frame, $, and the name of the column. So what we're going to do now is we're going to convert each of these 2 factor variables to a character variable. By the way, if we had made an error of syntax in doing this, or if some file didn't exist, you would see some sort of an error statement. Usually they come up in red. What I'm going to now do is, since I've changed the structure of those 2 variables, let's look at the structure of the whole data frame again. Whoops. Don't want it to. Look at the structure again. And lo and behold, notice these first 2 columns are now character variables. I really want the team ID and the league ID to be factor variables, and everything else are numeric in one way or another. By the way, you'll notice that any variable where it looks like all of the numbers are integers, is an integer variable. If you had decimals like down here, what you have are numeric variables. Okay. Often what you'd like to do in R is basically clear the screen. How do we do that? Basically, it's edit and clear console. Lo and behold, none of the variables went away, but the screen is clear down here, so now we can go further. How many columns and how many rows do we have? For a data frame, there is a built-in function called ncol and a built-in function called nrow, which gives you the number of rows and the number of columns. There are 24 rows, not including the header row, and 20 columns, so there are actually 20 columns of data. What are the names of these columns? There's another built-in function. It's called colnames. There they are. We're going to be interested in the HR column later on. Let's look at how I could capture that data again. Here's the name of the data frame, $HR. Just press enter or return. And there are 54 numbers. Now it's interesting, when you do this, this particular column is no longer a data frame. It's actually what we're going to call a vector. You really don't want to have to keep typing HRGTE50M $HR all the time. So over here, we're going to do an assignment. And we're going to put a new name, this little HR. This less than and a dash is called an assignment statement. You could use a plain old equal sign. So this says this column, basically, it's a vector, is going to be assigned to the variable called HR. And lo and behold, here's the same variables. Length of HR, 44. Remember, that was the number of rows in the data frame. If we wanted to sort these in ascending order, there's another built-in function called sort. And here's how we can work with these vectors. Basically, just make an assignment. But it didn't display it. There are a couple of ways to do this. For any variable, no matter what the structure, if you type its name and press enter, let me go back. I guess I'm going to have to put this back in. Type its name and execute it. You get the value of the variable. If you want to do the assignment and this value at the same time, you could do the assignment, but with an extra set of parentheses around it. And watch what happens now. Same thing. So we actually saved one command. For integer variables, or actually any variables that had categories also, The command table actually gives you a frequency table of the different values. This tells us that 7 people hit 54 home runs, 7 hit 52, 6 hit 50, only 1 hit 73. Guess that must have been Bobby Bonds. If we're unhappy with this because there are too many categories, we can actually use a command called cut that will break our categories into, I guess, different categories themselves. So watch what happens here. Something called cut. Notice what happened. You have 59 to 54, 54 to 59, 59 to 64, different categories. So each number of home runs, if we go up here, 54 is in the 49 to 54 category. 59 is to the 54 to 59 category. So basically, instead of numeric variables now, we just have a bunch of categories. We can now use the table command and lo and behold, it's a less granular frequency distribution of our home run data. If we have this, we can actually now display a bar plot of this data. Just bar plot, and table CT is actually the variable name. And you're going to see over here is our little bar plot. The graphics in R can be made to look very good, but you have to work at it. So this is a quick graph. What if I wanted to give a title to this and maybe a colors? Here's a command. Basically, it's almost the same thing. Now it says bar plot, y-axis, x-axis, the different categories. If I made this a little bigger, let's see if I can actually do that here. Let me zoom it. Notice if I spread it out, the categories are all listed. Otherwise, R automatically will handle what gets listed and what doesn't. Okay, a bar plot is best when you have categories of data. We just created the previous bar plot by categorizing the number of home runs in a season into different categories. We could even do a bar plot if we had things like eye color. And there the categories would not be numerical, but the idea of a bar plot would be the same. Now let's try some different data representation. The next thing I want to do is show a type of representation called a stem and leaf plot. In order to do this, the first thing I'm going to do is work with the 2 base hits, the doubles. They're spread out a little more than the number of home runs. So let me assign the variable x2b to, now notice again, we have our data frame. There was a column called x2b, data frame name, $, and the variable name. We'll access that column. I'm going to call it x2b. Then we're going to take the name, x2b, just press enter, and lo and behold, here are the number of doubles. And these are pretty well spread out because the number of home runs that a player hits is not necessarily correlated too well with the number of doubles. Now watch. This is called a stem and leaf plot. And here's what R did. Now notice each of these numbers of doubles are 2 digits. The first digit is going to be called the stem. And you notice the doubles range from a low of 16 to a high of 52. So what we're going to do is, well, what R did for us is it created a bunch of stems. Now you'll notice what it did is it has 1 stem for the 1s and then 2 stems for the 2s. It goes from 20, 21, up to 24, and then it starts at 25, 25, 26, 27, finally up to 52. It automatically created 1, 2, 3, 4, 5, 6, 7, 8 stems, but you notice a bunch of them are doubles. R will do this because its algorithm basically picks the number of stems that it feels would look best for representation. Let's suppose we didn't want doubles like 20 to 24 and then 25 to 29. All we could do is, if you look at help, and over here I'm going to just do help, STEM, and let's see what comes up over here. Here's help for stem, and notice there's a variable called scale. And here where we talk about the argument, scale controls the plot length. What does plot length mean? In this particular case, it means the number of categories. So what I'm going to now do is run the same thing, but I'm going to do scale equals 0.5, basically half the number of categories I just had. Let's run it. Okay, now here's how things work. The decimal point is 1 digit to the right of this, so it's over here. So this says the first number, the smallest number is 1, that's a 10 actually, and 6, 16. Another 16, an 18, a 19, a 19, etc. If you manually do a stem and leaf, the easiest way to get the representation that R has is to first sort the data and then just do your stem and leaf. It would come nicely then. What the textbook says is if you're going to do a stem and leaf and the data values are not in order, just pick a stem and put the leaves in one after another. The order here would not be sorted then, but according to the text, and it's actually true, the shape of the distribution would still be the same. For your homeworks, WebAssign will mark it incorrect if you don't sort it in this way. Similar to stem and leaf in terms of representation, we have, well, you call it a dot plot. And this is kind of interesting because different programs are going to call basically the same thing different names. In R, for whatever reason, a dot plot is called a strip chart. And let me actually create one. Here we have it over here. Notice the number of home runs, and this would be the number of people who have those home runs. I look at this. Now, most of these plots are totally adjustable. So if you look over here, you'll notice that the dots are a certain size. It winds up that CEX determines the size. What if I change that from 2 to 1? Let's run this again. Lo and behold, it's the same thing, but the dots are smaller. And it's pretty easy to interpret this. Once you have it, home runs 50, 1, 2, 3, 4, 5, 6. Exactly 50 home runs have been hit 6 times. 51, 1, 2, 3, 4, 5. One of the problems with graphs are they don't give you exact information, especially if they're hard to interpret. So over here, this is 54. Depending on how big the chart is, you might look at that and say, oh, that's 53. You'll notice because of the size, we have 50, then 55, 60, 65, 70. By the way, for whatever it's worth, for any plot in R, the argument main gives you the title. Notice main equals players at HR is players at HR. Next, we're going to create what's called a histogram. Now, a histogram looks like a bar chart, but a bar chart works with characters actually, or groups, really categories. A histogram will work with numbers. So the first thing I want to do is create a new variable BA. Now BA is actually batting average. Actually, let me actually display it now, BA. Let me run it and watch. You'll notice now we have 54 batting averages. And to draw a histogram is kind of easy. R will pick most of the arguments for us. The algorithm, once again, is supposed to create a well-designed histogram. Let's see what happens. Here it is over here. Whoops. Here it is. I mean, notice here the batting averages. And, for those people who do follow baseball, .26 would be called a 260 batting average. It's 260 over 1,000. .34 is a 340 batting average. So notice the batting average of 50 home run people, it seems to be centered a little over a 300 batting average. Can we make that look nicer? Sure. Let's look. Col means color. And what this does is it will make the total area under this 1. The shape will be exactly the same. And here you have this again. Histograms are very easy to create manually also. A little different from a histogram, but gives you the same information, is something called a density plot. Basically, R uses an algorithm to smooth out the histogram, essentially. You can even do the following with R. Let's do a histogram where the color is red. Now you'll notice with the density, we actually used a variable to define density, and then we plotted the variable. If you already have a plot up, lines will overplot that plot with characteristics. In this case, it's the density plot. Now notice here we have a histogram with a density plot overlaying it. A very neat plot is something called a box and whisker plot. Okay, let's clear the screen. Okay. Let's look at the batting averages. Now, what does summary do? It actually is going to give us 6 numbers. Min is the minimum of all of the elements in batting average. Remember, there were 44 of them. Max is the maximum. Median is the middle one. Basically, it's the number so that half the batting averages are less and half the batting averages are more. We'll talk a little bit more about that in a few minutes. The first QU is called the first quartile. Basically, first quartile is the value so that about 25% of the data is less than it, and around 75% is more. Third quartile is the opposite. 25% is more, and 75% is less. Look what the box plot does. Here we have this over here. And, well, I guess I can make this a little bigger. Oh, it doesn't want to let me, so I won't. Well, I can make it bigger. Okay, here's what happens. Here's a box. How is it created? The first quartile is the bottom line. You'll notice it's at around 0.28. It's actually 0.2878. The third quartile is the top of the box. You can connect this to create a box. The median goes through somewhere in the box. In this case, the median is above the halfway point in this box because there are more numbers up here than there are down here. Okay, now we have these dashed lines, whiskers, over here. This line, actually, let's go to the lower whisker. This would be the minimum value, which we see is around 0.26. Now let's look at the other side. It's a little more interesting. Ordinarily, this would be the maximum value. However, the distance between the first quartile and the third quartile, first, third, it's the side of this box, is called the interquartile range. Now, if you take 1.5 interquartile ranges from the top of the box, which is what we have here, and if there are no values bigger than that, then we let the top whisker, if you want, be at the maximum value. If there are more numbers above, which we have here, then this is 1.5 interquartile ranges above the third quartile, and these things up here with little unfilled in circles are called outliers. So it looks like we have 2 outliers in this box plot. Gives you a lot of information, actually. Some people do not like the box plot vertically. Well, in R, there's an argument called horizontal. Same box plot horizontally. Now, you can actually print parallel box plots in R. Now, some of these players who hit 50 home runs or more are in the National League and some were in the American League. So here's my box plot. Here's the BA we had before, a little tilde. You can read it as a function of. And then here we have the name of the data frame, $, and league ID. Remember, that was actually one of the columns. Watch what happens when we do this. And it's really neat. Two parallel box plots. This sort of shows that the American League batting averages are spread out more than the National League. It looks like the median is about the same for the people who hit 50 or more home runs. You can also plot one variable against another. This is called a scatter plot. If I take the BA, the batting average, and the home runs, and just plot. So batting average, HR, these are both numerical variables, and this is going to have the name scatter plot. Lo and behold. So these are the batting averages, and that's corresponding number of home runs. So it looks like when 73 home runs were hit, the batting average was around 330 something. When 58 home runs were hit, it looks like the batting average was around 380. Pretty high. It doesn't look like there's really too much of a relationship that shows up. Here's one. We're going to do total bases versus plate appearances. And you'll notice in this case, as the plate appearances increases, the number of total bases seems to increase. There seems to be a pattern. Now that we've shown some graphical type summaries, let's look at simple numerical measures of summary. The first thing is something called the arithmetic mean. Basically, the arithmetic mean of a set of numbers is just the sum of all of those numbers divided by the number of numbers you have. In our case, HR, there's the list of numbers. If we add up the 44 numbers and divide by 44, we'll get what's called the mean. Let's see how we can do that in R. But first, I'd like to mention something. What if we did not have the data frame to load in? What if we just had 44 numbers? How can we analyze them in R? And basically, R has a function. I called it the C function. Some people called it the combine function. Some people called it the concatenate function. And watch, I'm going to start here, and then I'll do it all over. HR1, assignment, and C is 54, 59, 60, 54. I'm going to stop here. Press enter. If I type HR1, because HR has the numbers we want already, you get the 4 numbers in the vector. If I wanted to extend HR1, the C again. But now watch. I'm going to put HR1 here, and then we'll do one more value. So this is 56. Now HR1 is the original plus the extra value. What this does is takes everything in HR1 already and just adds whatever we want after that. Now, watch what I'm going to now do. We're first going to just clear the screen. So here's my HR, and now watch how I define HR1. Let's get down there again. So here's HR. Here's HR1. Okay, now, manual entry really does have several problems. Number one, you notice it takes a long time. Number two, you can possibly put in the wrong values. But sometimes it's the only way to go. As a matter of fact, in many textbook homework type problems, you actually have to copy in the numbers from the problem statement. That's going to be the case in many of the WebAssign problems you're going to have. What did I say? I said the mean is the sum of the values. There is a built-in function in R that works on vectors that sums them up. Let's see what you get. Whoops. I pressed enter instead of control enter. Sum is 2446. The length is actually the number of values in the vector. That's 44. And if I take the sum divided by the length, which is 2446 divided by 44, you get 55.59. That's the arithmetic mean of the home runs for the of the number of home runs for the set of 44 that we have. Now, that's sort of a pain in the neck. It's better than doing it manually, but this is a statistics program. Wherever you have a statistics program, if there are common types of functions that are useful in statistics, there'll almost always be a built-in function in the statistics program. For R, if you want the mean of a vector, there is something called mean. Watch. We'll define this as MH. And lo and behold, same value. By the way, I think I've mentioned this once before. If you want to do the assignment and the display at one time, put parentheses around the whole thing. 55.59091 again. Now, the median is the middle value. Let me clear the screen first here. Okay, the median is the middle value. Now, depending on the length of the vector, the middle value could be two things. First of all, the middle value is the middle value once the data has been sorted. So here's V1, and here's sort of V1. And lo and behold, V1 had an odd number of elements. It's actually 5 elements. 1, 2, 3, 4, 5. Any vector with an odd number of elements, after you sort it, does have a middle value. In this case, the middle value is 5, and that would be the median of V1. If you have an even number of elements, you have a little bit of a problem. There's no middle. There are actually 2 values just off the middle. This is a 3 and a 5 in this case. In this case, you take the 2 middle values, add them up and divide by 2. Basically, it's the arithmetic mean of the 2 middle values after things are sorted. Once again, though, statistics program, there is going to be a built-in function called well, it may not be called median, but in R it is, a built-in function that calculates the median. Let's press enter. Well, actually, remember, command enter for me. And lo and behold, the same 5, the same 4, and the median of the home run values is 54, which is not the same as the mean of the home run values. They're just two different ways of measuring center. If you want to ask what the difference is, the mean is very sensitive to very extreme values because you have to sum them up. You're going to sum up a very large value or a very small value. So if you look at the mean of 5 numbers and the fifth number, the largest number is 2,732,000, and the other numbers are like 3, 4, 5, 6, the mean is going to be pretty large. The single large value will not affect the median at all. You think of how it's created. Now, if you want to still use the mean rather than the median, but get rid of the sensitivity, you can calculate what's called a trim mean. In R, the function for trim mean is the same as the mean function. We just have this trim value. And here's what R does for the trim mean. Okay. It takes the mean. In this case, this is a 2/44 trim mean. It takes the 44 values, takes away the 2 lowest values, take away the 2 highest values, and then find the mean of the 40 remaining values. Sometimes you'll see something like a 5% trim mean. What that would mean is take away the low 5%, take away the high 5%, and find the mean of what's left over. If you wanted to see what happens, I called SRT at some point the sorted value of the vector of home runs. Here we have it. Let's actually make sure I have it already. Oh, here it is. Okay. So if I take the vector, I can actually take individual entries of the vector. This is from the 3rd to the 42nd. That would be the first and the second entry were not there, and the 43rd and the 44th are not there. Let's see what we get. Same value. It took away the 2 highest and the 2 lowest. Here's a 5% trim mean, which should be somewhat interesting. R calculated the same value here, but 5% of 44 is 2.2. But R couldn't take 2.2 values away, so R's algorithm basically takes the number of elements it's taken away from the top and the bottom down until it's a whole number. Other statistics programs might handle this slightly differently, so you might get slightly different answers. As you might expect, there's going to be a maximum and minimum value. The built-in functions are max and min and R. Here's the median. And now let's look. We looked at the box plot before and the quartiles. Oh, did this again. Let me undo this. Okay. Okay, here are the home runs. The maximum value is 73. The minimum is 50. The median we saw is 54. Now, if you just use quantile home run, it's just going to give you the 0th, the first quartile, the median, the third quartile, and the maximum. Built-in function. If you do quantile HR and then a comma and then some decimal, less than 1, it's going to give you that percentile. I guess R would call them quartiles, but humans call them percentiles. So if you wanted to find the 30th percentile of HR, it's quantile HR, comma, 0.30. Um, what we've looked at just now, mean, median, and trim mean are measures of location. We can also calculate measures of how spread out the data is. These are measures of variability. Here's one. The range of a set of data is the maximum minus the minimum. Now be careful. In R, if you do range of a vector, you're going to get a vector, which will be the minimum and the maximum. The statistical definition of range is actually the maximum minus the minimum. Now you'll notice range HR is actually a vector. So the first element is range HR and then a bracket 1. That's element number 1. And this is range HR element number 2. Notice first element, second element, 73 minus 50 is 23. Quantiles are a measure of how spread out the data is. And we've seen this before with the box plot. Box plot's kind of interesting because it is really a measure of location and a measure of variability. So here are quantiles, the first quartile, 25th quantile, median, 50th quantile, or 0.50, and the third quartile, or the 75th percentile. Now, in terms of terminology, this would be called the 75th percentile, the 50th percentile, the 25th percentile. And the interquartile range tells us basically how wide apart the middle 50% of the data is. Notice, it's a function, capital IQR. Most built-in functions in R are lowercase. IQR happens to be uppercase. And it's this computation. It's the third quartile minus the first quartile. The same value. Now, the next measure of variation is something called the variance, or its square root, the standard deviation. And we'll see how to calculate this. So, let's clear the. Let's actually look. So here are the home runs listed, and here's the mean. How far is each of these values away from the mean? In R, if you have a vector and you subtract a number from it, mean HR, a single number, R does element by element subtraction. That would work for addition, multiplication, etc. So notice, this first value is 54 minus 55.59091, negative values. And I call this variable HR diff. Now, it winds up, if I added up HR diff, all these values, well, actually, to do it down here, I don't have it in my computations, sum HRDIFF, I'm going to get 0. Now, R does all computations in floating point. Notice this is times 10 to the minus 13th power. It doesn't do exact arithmetic. Essentially, this is 0. You have to watch this whenever you do a computation in R. Sometimes you get this scientific notation with very, very negative exponents. It means it's 0. The next thing we're going to do is we're going to square HR diff. Now, what does that do? It actually takes each of these values and does element by element squaring. So now I have a bunch of positive values. It won't sum to 0. So the computation for variance now says sum these up. And this is my sum of the squares. It's 1,334.636. The length of HR minus 1 now is going to be used as a denominator here. I get 43. And now what I do is I take the sum of the squares and divide by the length minus 1. And that's called the sample variance, which in this case is 31.03805. The square root of the sample variance is called the sample standard deviation. These are very important numbers in R, and this probably took us, 5 minutes to do. Watch. We have the two values. Same two values, built-in function var gives the sample variance of a vector. SD gives the sample standard deviation of the vector. And that is the end of this video.